Ladies and gentlemen, welcome to this fifth lecture about the fast design rules for seismic isolation systems. I think that this is a very important lecture because we will see actually the main hypothesis that we have to assume at the beginning in order to get a very initial design of the overall devices that we have to consider within our isolation system. So before starting, I want just you to ask some questions about if you have about last lectures. Is there anything which was not clear? Okay, if not, I start sharing my screen and I go forward with the presentation. Actually, we can say that this is the first week of this short course. Actually contains the whole theory that we have to use. And then next week, all the lectures will be focused on practical applications for the design of a case study structure. We will do actually a finite element model of the structure through the software SAP 2000, and then we will try to carry out a nonlinear time history analysis for the seismic assessment of the structure itself. So let's share our screen. Okay, and let's start with this lecture. And as I mentioned, all the contents of this lecture has been published within this article, this research article in the Vibration Journal. It is an open access journal by MTPI. And it has just been published and actually provides all the information and maybe some additional information which will not be delivered within this presentation. So I have just uploaded the PDF file of the article in our shared folder so that you can go back and see all the details. But all the details which are contained in that article are nothing less than what we will be discussing today. So we have to start by considering some simplifications of the overall system, simply because we just need to pre-design our isolation system. We will come up with dimensions and mechanical properties according to a given behavior that we will assume at the beginning. And so since everything is simplified because we have just to come up with a first guess of the definition of the isolation devices, we can just consider a simplified version and model of the overall structural system. And among all the strategies that we can adopt for simplifying actually our system, we consider the base isolated structure as a single degree of freedom oscillator. And the main assumption is focused on what we have discussed in the very first lecture of this short course. If you remember, we assumed that the building has a single degree of freedom oscillator and the isolation system exactly like a linear elastic spring. And so we discussed about the possible hypothesis that we can consider by neglecting the mass of the actually of the plate, of the reinforced concrete plate. And so we get actually a series of two springs, and we were able to compute the equivalent spring of just this series, and it was approximately equal to the stiffness coefficient related to the isolation system, simply because we are expecting to find the stiffness of the building much higher than the stiffness coefficient associated to the isolation system, simply because we needed to provide the proper period shift. And in order to do so, we have to enlarge the period, and to enlarge the period, we have to reduce the overall stiffness of the system. And so we have just to add an additional layer, which is actually our isolation system. with a lower value of stiffness, global stiffness coefficient, let's say. So we are sure that the stiffness associated to the building is much higher than the one related to the isolation system. So this is a very simplified system. I'm sorry, here there is Italian sistema di isolamento, but it means actually isolation system. And this means that the overall assumptions that and the overall results that we will get at the end of our design rules will be checked afterwards with specific and detailed analysis, for instance, nonlinear time history analysis. And this is actually what we are going to do next week with the SAP 2000. But actually, at this moment, we just need to start with the design of the single devices. And as I mentioned in the previous lectures, we will see at the end of this short course that this assumption, that is by considering the overall structure, the base isolated one, as a single degree of freedom oscillator, this assumption does not lead to significant differences with respect to the real response of the overall system, may be returned by a more detailed analysis, for instance, the nonlinear time history analysis. We will see a comparison actually the last 2 days of this short course, where we will compare. We will be comparing the displacement time signals at the isolation system returned by the nonlinear time history analysis performed on the full 3D finite element model. And we will compare these to actually the outcomes of the time integration of a single degree of freedom oscillator. We will learn how to model a single degree of freedom oscillator in a non-linear way. So this means that we will be able at the end of the short course to model the proper hysteretic loops for all the typologies of devices that we have considered up to now. So rubber bearings, leather rubber bearings, and curved surface sliders. So I will provide you very fast and easy to implement rules which are actually able to describe the proper hysteresis of the overall force response. And we will be comparing all the displacement and the force response. And the old procedures, related to all the typologies of devices, are based on the same assumption. So the aim of this research study was to provide very fast and easy to use rules to design isolation devices, but with very easy initial assumptions, which could make actually these rules to be usable for practitioners and at any levels of complexity for any projects. So the main assumption, the main initial assumption is related to the performance point of the overall structural system, which is directly related to two components which are very important. The first one is the design period of the overall system, and the second one is the equivalent viscous damping, which actually rules the energy dissipation capacity of the overall isolation system. And according to the definition of this performance point, we have seen that for instance, the design value of period has to be chosen by considering the minimum period value for considering actually the seismic isolation. We have seen that we have to guarantee that with the design period, we will go through spectral coordinates with respect to the acceleration values, which are significantly lower than the one returned by the fixed base configuration of the building, so that we have actually some effective solution to reduce the vulnerability, the seismic vulnerability of the structure. And then we have seen that the equivalent viscous damping is directly associated to the energy dissipation capacity of the system, and the equivalent viscous damping ratio, the numerical values, I mean, are directly related to the typology of isolators that we are going to install. So we have seen that for rubber bearings, we have two typologies of isolators, which are actually the low damping and the high damping. And according to these two typologies, we have different values for the damping ratios, which are actually from 5 to 10 for low damping, and for between 10 and 15, maybe 20 for some innovative rubber compounds for high damping rubber bearings. And we have also seen that the damping coefficient, the damping ratio can be considered as a constant value for rubber bearings, since we generally design the devices for a shear strain which is higher than or equal to 100%, and so we generally 100% is the key value for design rubber bearings and also lead rubber bearings. So this means that the height of the overall device is actually equal to the displacement demand, since the shear strain can be computed as the ratio between the displacement demand and the height of the isolator. If the ratio is 1, which means 100% of shear strain, the displacement demand is actually equal to the height of the isolator. And according to these, to all these definitions, so according to the definition of the performance point, we can consequently compute what we generally call the global characteristics of the seismic system, the seismic isolation system, which are these three characteristics: the equivalent isolation stiffness, the displacement demand, and the normalized force demand. And actually, all of them can be computed according to other aspects with that have to be initially guessed. So for instance, the equivalent isolation stiffness, which could be called KIS, is directly returned by the definition of period. And this is one of the key parameters for the definition of the performance point. So the period T isolation can be returned by the general expression for the period for a single degree of freedom oscillator, which is 2 pi times the square root of the total mass, which is above the isolation system, and the stiffness of the isolation system itself. So we can get actually the expression for the equivalent stiffness of the isolation system, which is the total mass, which is multiplied by 2 pi over T isolation squared. And this is actually omega squared. And with this equation, we are able to compute the equivalent isolation stiffness, and note that this value of stiffness has to be related to just isolation devices. So whenever we will deal with the hybrid solutions, which means different typologies together of isolation devices, and generally we have them whenever we deal with rubber bearings rather than lead rubber bearings, because actually we will get at the end of the design procedure a number of isolators which is lower than the total number of structural supports of the building rather than the structural system. So it means that we need a hybrid solution, which is just a combination of rubber bearings or lead rubber bearings and flat sliders in order to cover all the structural bearings points. And What I meant is that this K isolation is just related to isolation devices. So in the case of a hybrid solution, so both the combination of rubber bearings and flat sliders, this K isolation is just related to rubber bearings. And the same for the case of lead rubber bearings. The equivalent isolation stiffness is just related to isolators and not to flat sliders. We have seen that the standard code for testing anti-seismic devices actually lists the flat sliders as seismic isolators, but we have already discussed why we don't really consider flat sliders as seismic isolators, simply because they don't have any kind of recentering capability, because they are just represented by a purely frictional response. So with no influence of the flat sliders, we will have actually just the equivalent isolation stiffness for the rubber bearings rather than lead rubber bearings. Then the displacement demand will be considered as the spectral coordinate of the spectral displacements with respect to the isolation period and the design value of equivalent viscous damping. And this is actually part of the what we call the performance point. This is the displacement part, so the displacement demand, and then we have also the normalized force response, which is actually normalized force demand, which is the spectral acceleration coordinate. So this means that we have SA of the isolation and design equivalent viscous damping. Okay, so these are the main characteristics, let's say global characteristics of the isolation system. Then we have actually to smear among all the implemented devices, all these characteristics, and I just want again to highlight that they will be smeared just among the isolation devices and not to also to flat sliders when we have to consider hybrid solutions. And at the beginning, we just assume that we consider isolators with exactly the same behavior. So this means that we will have same constitutive law, which means same hysteretic rules, and same mechanical properties and same geometry for all the isolators. So this means that we will get, we will come up with actually the design of such isolation system, and then maybe if everything looks like not working properly, we can change some device in order to achieve the optimum of the isolation system. And then the total number of structural bearing points has to be evaluated, because it is a key reference value for us, because we have to cover all of them. So if we get at the end of the design procedure a number of isolators which is lower than the actual structural bearing points, we will have to cover all the remaining points with the flat sliders. And this is actually what is written in the third point, and we will have to consider flat sliders with a very low friction, which will allow not to mismatch the overall response with respect to the very initial assumptions. And this is what I mean. This is actually a plan view of a building, of the isolation system below a building. And you see these are the gray dots are elastomeric bearings, rubber bearings, and the black dots with the arrows are flat sliders. Okay, so you see that flat sliders are just made up of straight and flat sliding surfaces, which are actually stainless steel sliding surfaces with innovative and low friction sliding materials, which is actually this one. Okay, this is a pad, a sliding pad of an innovative sliding material. And here we have also the main assumption that you have to consider for the isolation system, which is actually to provide the overall layout for isolation devices, which is actually by considering isolation devices located at the corners and at the edges of the overall structural systems in order to increase the torsional stiffness of the overall isolation system. So now we have to start with the elastomeric vector. Let's start with the very first technology that we have considered, and this is exactly the same slide I've shown in the first lecture, just to remind the main characteristics of this typology. We can have different rubber compounds characteristics, which are represented directly through the value of shear modulus. We have soft, medium, and hard compounds with increasing value of shear modulus from 0.4 to 0.8, 1.0 for the medium, and then the maximum value, which is 1.4, 1.5 megapascals. And I just want to remind these numbers because actually these are some values that we have to guess initially, and now we have to guess them just because we want to carry out a theoretical design. But generally what happens is that you go to a producer and you ask for characteristics of this the rubber compound. Okay, generally they have medium to hard, but there are also some applications where the soft compound could be useful. And given those characteristics, you can go forward with your design, and then maybe you come up with the geometrical and mechanical properties of the devices, and then you go back to the producer to ask if the design device is already listed within catalogs which are provided by the producer itself, rather than it is a custom-made device. And generally, custom-made devices can be actually produced by companies. They obviously cost a lot more, but because they are custom-made and they are not just listed in catalogs, because whenever you produce a new device, a new custom-made device, you have to ask for CE mark. So there are a lot of additional procedures, administrative procedures, and testing, additional testing to provide evidence that what is designed actually corresponds to what to a realistic behavior, the experimental behavior, what is designed actually corresponds to the initial design assumptions. Then there is the shear strain at maximum displacement. This is another very important parameter, and we have considered 100% as a lower bound, since we want to have a constant value of shear modulus for the compound, and also we want to consider a constant value of equivalent viscous damping ratios. And values, as we have already mentioned, for low damping are from 5 to 10% of damping ratios, rather than high damping, which goes from 10% to 15% and 20% for very hard compounds. So let's start with the procedure. You will see that these three steps are actually in common with respect to all the bearings that we can design: rubber bearings, lead rubber bearings, and also for the curved surface sliders. because this is actually the main hypothesis for these fast design rules, which is the computation of the minimum isolation period. And this is what we have discussed in the first lecture. So how to compute the minimum isolation period, and actually with respect to that value of period, we will have actually no improvement between the isolated structure and the fixed base structure. Okay, so because actually we have exactly the same spectral coordinate in the acceleration spectrum, and this means this can be directly associated to the base shear of the overall structural system, so there is no improvement. But as we consider a higher value of isolation, of design isolation period, we will get a lower value of the spectral coordinate for the acceleration spectrum, and consequently we will get lower values of base shear, and consequently again we will gain lower internal forces for all the elements. So the computation of the minimum isolation period is fundamental for the choice and the assumption of the design performance point, which is in terms of isolation period, which should be much greater than, let's say, than the minimum isolation period, and the equivalent viscous damping. So for what concerns the equivalent viscous damping, we have just to choose the numerical value according to the typology, the technology of isolators that we want to consider. So for rubber bearings, depending on low damping and high damping, we can assume certain values. For lead rubber bearings, we know that the damping ratios is bounded between 20% to 30%, because the dissipation capacities are extremely higher with respect to rubber bearings. For the same can be assumed also for curved surface glider, even though we have seen also experimentally that we can get up to 40% and 45% of equivalent viscous damping, strongly depending on the friction coefficient value. And finally, there is the computation of the displacement and the normalized force demands. So the displacement, as I mentioned before, is represented. The displacement demand is represented by the spectral coordinate displacement spectrum as a function of the isolation period, and as a function of okay, eta is the reduction factor, which is in the Italian standard code, is something like this, where C design is actually the damping ratio. So that is a reduction factor for the elastic spectrum, which provides the scaling effect of the response spectrum with respect to increasing value of damping ratios. You see that damping is in this formula has to be considered as a percentage and not as a pure number, because you see this scaling factor eta should be equal to 1 whenever we consider the viscous damping ratio equal to 5%. So the only way to get 1 with the 5% is to consider CD directly equal to 5 and not equal to 0.05. So just in this equation, we need to consider C. So the equivalent viscous damping ratio has just a percentage and not just a pure number. And the same, according to the definition of the spectral displacement, we can get the pseudo acceleration coordinate just by multiplying the displacement demand times omega squared, which is 2 pi over the isolation squared. Now we start with the steps for design directly related to the rubber bearings. So the fourth steps, you will see that there are very few steps for designing these devices. The fourth step is already provides a geometrical quantity for the device, which is the height of the isolators, and the height can be computed by assuming a numerical value, a design numerical value for the maximum shear strain at maximum displacement. So you see, if we consider the maximum shear strain equal to 100%, we will get what we mentioned before, the height of the device directly equal to the displacement demand, rather than if you consider a higher shear strain, and so you want to displace the device much, more than what the length of his height, and so you will get a smaller height with respect to the lateral displacement, according to this expression. And I just want to highlight that according to this definition of the shear strain, the deformation has to be considered like this. Okay. And this is the displacement, the max, and the max is directly the spectral coordinate with respect to the displacement spectrum, the height of the isolator, H isolation, and the ratio between the displacement and the height is this angle here, which is gamma, which is actually the shear strain. Okay. So according to this definition, we can come up with the first geometrical quantity, which is the height of the device. Then in the fifth step of the procedure, we can come up with the last geometrical quantity of the device, which is actually, okay, here I say the plane diameter of the device, because I'm assuming that the devices will be cylindrical. But there are a number of applications, real applications, where devices, rubber bearings, are actually with a rectangular rather than square section, horizontal section. So you can consider diameter rather than the overall sizes of the general shape of the horizontal section. So if we consider the diameter, we can estimate the diameter by doubling the displacement demand. This is just because we want to avoid buckling and rollout behaviors of the bearings. So what I mean is that if we displace actually too much our isolator, what we want is to provide a sort of rubber column to provide actually reaction with respect to the vertical loads. Okay, there should be a superposition of areas and overlapped area between the plates of the isolator itself. Also, because if we can consider another situation where we have the diameter of the device exactly equal to the displacement, we would get exactly like this, a situation like this. Okay, you see that here we still have the application of vertical loads. We also have the application of shear because it is displaced, but here you don't have any overlapped area. Okay, so you have the overturning of the device, and you have buckling. So the buckling is directly related to the collapse of the and the failure of the device. So this means that you are losing actually the vertical restraint at that location. So this automatically means that this induces also the overall collapse of the overall system of the overall building, because you are missing, you are losing actually the vertical restraint. So there is automatically a set of internal forces which surely exceed the design limits within maybe also the reinforced concrete plate. There are bending moments and shears which are highly overestimated, underestimated, I mean, in the design phase, because actually the static scheme of the plate has been changed by this situation. So this is just a very straightforward rule, just to consider the external diameter as twice the displacement demand. But actually, it works for the most part for the most numbers of applications. And then these are the final two steps for rubber bearings. So we have 7 steps, and 3 of these steps are just in common with respect to all the other devices. So if we have the whole geometry of the device, so it means that we have the cross-sectional area and also the height of the rubber portion. So we can compute the single device lateral stiffness as the multiplication of the shear modulus and the area, the plane area, divided by the height of the isolator. And obviously, this is related to the compound characteristics that we assume in design. So compound. Okay. By assuming the compound characteristics, we have the G value. Okay. And by assuming the G value, we can compute the single device lateral stiffness. And finally, we can compute the total number of isolators simply because at the very first steps, we have defined the performance point. And if we have computed the performance point, we have also the numerical value of the isolation period, which means that what is called GESI, so the equivalent stiffness for the isolation system, is equal to, again, the total mass, which is above the isolation layer, multiplied by 2 pi over the isolation period. I mean, okay, design rather than IS. Okay, it's the same, squared. So this is a global characteristic, okay, of the all isolators, okay, not flat slider, but just isolators. So in order to come up with the number of isolators, we have just to divide the total, the global stiffness coefficient by the single device lateral stiffness. And so we will come up with a number, and obviously the total number of isolators makes sense even if only if it is just an integer. So we have to round it, and maybe we can discuss if it is better to I mean, to seal it or to floor it, but generally what you can just round to the nearest integer, and so the final result will be the proper one. What it means is that okay, you have to round this number, but you have to keep in mind that maybe the overall system should be at least symmetric in order to provide the best behavior of the overall system. So maybe it is better to provide I mean an even number, okay, and to avoid odd numbers, because odd numbers maybe we get some isolators, at least one isolator, which cannot be placed easily in the plan view in the layout of the isolation system. So it is better to get and to round the overall result for the total number of isolators to even numbers. If it is not possible, or if the next even number is quite far away from the result that we get, maybe we can just go back in our procedure to change some numbers, some initial assumption in order to come up with the optimum of the definition of the isolation system. The best application of these procedures, all of them, also the ones related to lead rubber bearings and curved surface sliders, is just to apply them within an Excel spreadsheet so that you can then change some cell with some different assumption for maybe the compound characteristic rather than the lateral shear strain of design and so on, and then to come up with the best solution for your application. So I think that then we will start with lead rubber bearings. For concerning rubber bearings, do you have any question? Okay. If there is...
Sorry, Doctor.
Yes.
It is not for rubber bearing, but just for the formula of the mass total. In here, we are assuming that distribution of the gravity load coming on each single bearing is same because of the height of the rigid foundation, isn't it?
Well, actually, the vertical stiffness of rubber bearings is very high with respect to the horizontal one. It could be in the order of 2,000 meganewtons over meters. So generally, you don't pay that much attention on the vertical reaction applied at all the devices. And actually, this is a typology of bearing which actually provides a lateral force response, which is uncoupled with respect to the axial force. And this is obviously, you are perfectly right when we deal with the curved surface sliders, where actually we have differences in the force response induced by the vertical loads. But actually, that is another case because also that is the only case. The curved surface slider case is the only case where we can just design a unique typology of device for all the supporting points. But here we will surely need to consider hybrid systems, which means a coupling, a combination of flat sliders and rubber bearings.
Thank you, Doctor.
Is it clear? Okay, perfect. Okay, so other questions? So you see that it is quite straightforward, quite easy. There are very easy assumptions based actually on the general parameters that are assumed, which are assumed in design. And maybe the main parameters that we have to guess are actually the maximum shear strain, but generally it is equal to 100%. And then you just guess twice the displacement demand for the computation of the flange diameter, and then you have obviously to assume a certain compound characteristic in terms of shear modulus, and that's it. What is a little bit more complicated is, as you can imagine, the fast design rule for lead rubber bearing. But again, we have performed some statistical analysis on the database of real tests performed at the laboratory of Center Foundation. I actually performed some analysis in order to come up with some guidelines on the main parameters to design this typology of devices. And so again, we want to just briefly remind all the main parameters, which are actually the same, maybe the same of rubber bearings. We have just some additional parameters, which is, okay, here it is mentioned, the yielding shear strain, which is bounded between 2 and 7%, but we will discuss a little bit more in detail about this parameter. We are talking about yielding because the lead rubber bearing is a rubber bearing with an additional contribution, which is provided by the lead core. And the lead core is an additional, in addition, which provides actually a much higher energy dissipation capability, and actually the overall behavior of this device can be modeled through an elastoplastic without any hysteretic rule. So let's go through all these steps. But before considering the steps for designing, we have to consider the overall behavior. As I mentioned just a few seconds ago, we can consider the elastoplastic behavior with hysteresis, obviously. for the force response of such isolators. But in order to come up with the fastest design procedure with the very few steps and some statistical analysis, I had to switch from the general definition of elastoplastic behavior to this actual diagram, which has exactly the same meaning. But if you see, I have just normalized both the axes with respect to the same quantities located at the yielding point. So this means that this is a force displacement loop, and I have normalized the horizontal axis with respect to the displacement at the yielding point, and the same has been done for the vertical axis. So the force axis has been normalized with respect to the force at the yield point, the yielding point. So this means that this diagram, the second diagram, this one, has a yielding point which has coordinates 1 and 1. Okay, just because of the definition of the normalizations for both the axes. And then the maximum displacement point can be defined according to two important parameters. The first one, the first coordinate, the horizontal coordinate, is represented by the displacement ductility. So the ratio between the maximum displacement and the yielding displacement. And the displacement ductility for this typology of devices can achieve actually very large values. But this is simply because the yielding displacement can be very small, as we are going to see in the next slides. So this means that the maximum displacement could be very large because we are providing period shift. Okay, we are also providing energy dissipation there, so we are trying to limit actually the maximum displacement, but in comparison to the yielding one, the maximum is very large, and actually the displacement demand could achieve also values up to 50. And for what concerns the vertical component of the maximum displacement point in the second diagram, we can call it overstrength ratio. And it is actually the ratio between the maximum force and the yielding one. And it is just an overstrength because which can consider it as an overstrength because it is actually the increasing the strength of the isolator induced by the rubber compound, because we know that the plastic stiffness, the post-yield stiffness is directly related to the rubber behavior, whereas the yielding force is directly related to the yielding behavior of the lead core. So according to this definition of force displacement loop, so according to the definition of the normalizations for both the axes, all these steps for the fast design procedure are straightforward and very easy to use, and you will see what I mean. So the first three steps are always the same as for all the other typologies of devices. So the first is, again, a computation of the minimum isolation period, because we should know the lower bound of the design period for our system according to the fixed bay configuration of the building, and especially with respect to the spectral coordinate induced by the self period of the first mode, of the first vibration mode, and the behavior factor of the fixed configuration. According to this lower bound, we can then assume the performance point in terms of isolation period, the design value, and the equivalence viscous damping ratio. And according to this typology, so lead rubber bearings, we can assume the equivalent viscous damping ratio equal bounded. I mean, bounded between 20% and 30%. We have to assume a single value, and then to go for all the other steps. The power, I mean, let's say, of this procedure and the is that actually they are easy to implement through an Excel spreadsheet. So this means that you can just assume an initial value of equivalent viscous damping, and then you can change it in order to see what actually what is actually the influence of the equivalent viscous damping on the overall sizes and mechanical properties of the device that you can obtain. So you can just perform some parametric study on the design, and it is very useful when you have to come up with the best solution of your isolation system. And then again, the third step, so the computation of the displacement and normalized force demands in terms of spectral coordinates for both displacement and pseudo acceleration. And remember, okay, here it is not written, but generally we can say that the third step is the computation of the global characteristics of the isolation system. So together with the displacement demand and the normalized force demand, you should also compute the equivalent stiffness of the isolation systems, like m dot times 2 pi over the design value of period squared. Okay, so the third step is always the computation of the global characteristics of the isolation system. Then the fourth step is exactly equal to the rubber bearings. So you compute immediately the first geometrical quantity for the device, which is the height of the device. So according to the design value again of the maximum shear strain, and again we generally assume 100% of the lateral shear strain. Then there is an innovative, not innovative, a new information that we need for lead rubber bearings with respect to rubber bearings. For lead rubber bearings, due to the lead core, we need also the definition of a yielding point. And so we can compute the yielding displacement, and it can be estimated through this equation, which is exactly similar to the previous one, but the previous one is related to the maximum displacement, whereas the second one for step 5, this expression is directly associated to the yielding point. And actually, it looks meaningful to consider actually the deformation of the lead core as a shear strain, also related to as it happens for the maximum displacement. So my initial question when I started by considering this research work was actually to carry out a statistical analysis of the whole data set of real tests performed on isolation devices, full-scale and isolation devices here in Pavia, in order to come up with maybe a statistical distribution for some parameters. And one of them is actually the yielding strain, the yielding shear strain. And what I did is it was quite hard because you have seen also in the numerical laboratory the worst thing to deal with when you have to carry out data processing is to write actually to implement a script in MATLAB, which is the most general one for any kind of tests performed also in many years. So because I considered, I think, 10 years of tests at the laboratory. So the main script that I've developed was actually able to consider all the dynamic tests, all the cycles. This is the first, the second, and the third cycle of a given test. You can now you can recognize this name, repeated cyclic. Because we have considered these also in the numerical laboratory, and this is exactly the same figure that I've shown also in the first lecture. Now you know the meaning of RC, which is repeated cyclic, which is provided by the European Standard Code for anti-seismic devices. And the script actually was able to isolate each cycle for each dynamic test, as we did. But I also implemented a nonlinear best fit procedure in order to come up with a bilinear constitutive law, which is actually representative of the same dissipative capacity of all the hysteretic loops, and also not only the hysteretic capacity, so the hysteresis area, but also the representative of all the actual points. So this is just an ad hoc least square procedure for all the tests and all the cycles. And then in order with the definition of bilinear constitutive laws, it was very easy to consider the yielding displacement and to compute the ratio of the yielding displacement with respect to the height of the isolators, of all the isolators. And this is actually what I got. This is the distribution. Firstly, I got the bar plots, obviously. And then by looking at the from the quality point of view, the bar plots, you can just notice that the overall shape of this distribution could be addressed to a log normal distribution. And also the I also provided in the paper that you had, I've just copied the PDF file of the paper within our shared folder so that you come up, you can go back and come up with all the details. I also provided a best fit procedure in order to compute the R squared for the log normal distribution, and I got something like 95% of R squared. So this means that the fitting is very good. And together with this, once you have to deal with the log normal distribution, you have 3 individual values for mode, median, and mean. The assumption that I generally assume for design, and this is what is written in the article, is to consider in design the mode value, which is generally the most frequent value. So the peak of the actually of the probability density function. So this is the mode, and the mode is 2.5%. So this means that the yielding displacement can be computed once you compute the height of the device as 2.5% of the height of the device itself. Okay, and this is the most frequent point of the distribution of the probability density function. And we have to keep in mind that this parameter has actually a distribution, a probability distribution. And this means that it is not a deterministic value, but it can be represented by a random variable. Okay, so this means that maybe you can just assume for an initial design 2.5%, but then you can also vary that parameter according to this distribution. And consequently, you can have a parametric study, and you can observe also the variation of the final result in terms of geometrical and mechanical properties of the devices by considering the variation actually of this parameter. Okay, I can already say that because we have studied also the variation of this parameter and also the other parameters that I'm going to mention later on the overall response of a base isolated building. And also I consider it also for bridges. I can ensure that these parameters of the yielding strain, the yielding shear strain, does not provide significant difference if you consider it as a variable, as a random variable. So if you change that number, you don't get actually a significant difference with respect to the mode. Okay, just because this is 2.5% is already a very small value with respect to the maximum deformation, which is 100%. And this means that on the hysteresis of the device, this provides a very low influence. For instance, on the force response rather than the hysteresis area. Okay, so this can be generally assumed as a deterministic value simply because if you consider it just as a random variable, you don't get so much difference in comparison to the mode, to the assumption of the mode value. So I know maybe this is you may have questions on that. Is there any question? Okay, good. I just want to highlight this. Now we know, I go back to the previous slide, the 4th and the 5th step. We know the height of the device because we have guessed, for instance, the maximum shear strain equal to 100%. Okay, and then now we know that the yielding shear strain can be assumed as 2.5% because we have the statistical study of dynamic tests performed on full-scale devices. So we know that the mode value is directly associated to 2.5% of lateral yielding shear strain, and so automatically we have the yielding displacement. So this means that we can compute the displacement ductility because we have the maximum displacement, which is the spectral coordinate for the displacement spectrum, and now we have just computed the yielding displacement. Okay, so after let's say or within the fifth step, together with the yielding displacement, we can also compute the ductility demand with respect to displacement. Okay, and this will be useful. This value will be useful for the sixth step, because through the definition of the equivalent viscous damping ratio and the displacement ductility demand, and this is what I meant, we can compute the overstrength factor. Okay, this is the expression, and this expression that doesn't appear in Magic, but it is actually it actually comes from the definition of the equivalent viscous damping, and this is what I meant with the easiness actually of the overall steps that I have obtained to directly associated to the force displacement loop in a normalized, considered as a normalized with respect to the yielding point. So this is a very simple equation according to that diagram, which is actually related to the equivalent viscous damping, and then you just collect the overstrength factor and you come up with this expression. So according to the displacement ductility, which is again d max over the yielding displacement, and we have already them because the first one is the maximum displacement is the spectral coordinate in displacement spectrum, and the yielding displacement is what we have just computed according to the distribution of the yielding shear strain. So once we have the overstrength and we know that, as I mentioned in the previous slides, the value is bounded between 1.5 and 3 generally. Then we can come up with the geometrical characteristics of the lead core, and then we can estimate the yielding force of the lead core. And in order to do this, we have to study again the statistical analysis of two additional parameters, which is actually the yielding stress of the lead core. Okay, and just if there is a ratio, a common ratio between the diameter of the internal lead core and the height of the device. Okay. So this is just this assumption. The diameter of the internal lead core divided by H isolator. So let's talk about them. The first one, the shear stress for the lead core related to the yielding point. Once I have observed that there is actually a distribution, a probability distribution for the yielding shear strain, I tried actually to consider also a distribution for the corresponding stress. So maybe there is actually a distribution and a given behavior for the shear stress for the lead core. And I've seen that at this step that the overall procedure would be very easy if we had the opportunity to compute the geometrical section of the lead core. So I tried to see if there was a correlation between the diameter of the internal lead core and the height of the device. And this is actually what I have obtained. And these are okay. Relating to the shear stress. This is actually the same study of the bilinear constitutive law, the best fit actually, nonlinear bilinear constitutive law considered for all the tests that we have performed here in Pavia. And we see that again, the overall bar plot can be associated to a log normal distribution. And again, here maybe we have the highest R squared value for the best fit procedure. And the mode again is the reference value, which is directly related to 11 megapascals. And then we have also the distribution, again, log normal for the ratio between the lead core diameter and the height of the isolation device. So here we have, this is, I think, the probability density function with the highest R squared value for the nonlinear best fit procedure, but the highest was actually 86%. So fair enough to consider this as the proper distribution. And we can see that the mode value for this distribution is actually 0.8. Okay, this doesn't mean that for all the isolation devices that we will find also in catalogs for producers, you will find that the diameter of internal lead core will be 80% of the height of the device, because it strongly depends on the quality of the materials. I mean, not the quality, but the actual mechanical properties of the material of the lead, and so on. So this means that you can actually find these all these values from 0.5 to up to 2. Yeah, 2 is very very low. So I think that between 0.5 and 1.5, okay, as are the most probable values. But generally, this is at least the most frequent in the applications, and these are actually observations, a statistical, I mean, a statistical set of data related to full-scale devices, really tested in the laboratory. So this means that they are quite realistic. So once we have the yielding force, we can come up with the maximum force of the single device, just multiplying the overstrength times the yielding force, okay? And according to the maximum force of the device, we can also come up with the area of the rubber portion, and then to come up with the external diameter of the device. Because remember that in the force displacement loop for lead rubber bearings, we have the elastoplastic with hardening, and the hardening is directly related, which we can call it KR, because this is directly related to the response of the rubber portion, okay? So F max minus Fy divided by d max minus dy. This is the differential quotient for the Kr, and Kr can be computed as the rubber bearing solution. So for G times A, which is the actual our unknown, divided by the h of the isolator, the height of the isolator. And A is related to just the area of the rubber compound. So this means that if we look at the area, the horizontal area of the device, we have the external diameter, which is actually our unknown. And then inside we have the diameter of the lead core. So the area that we are mentioning here is the area of just the rubber compound. Okay, so this is the area. Okay, now I can't do undo for comments. Okay, so this is the area that we need. Okay, and so generally we come up with the area with this expression, and then according to this area we can compute the external diameter, which is equal to the square root of 4 times the area over pi plus the diameter of the lead squared. Okay, and this is the lead core. So first of all, we have to compute the stiffness of the post-yield stiffness, which is directly associated to the rubber compound, by using the differential quotient. And then according to the KR value, we can compute the A, and then with the A, we compute the external value, the external diameter of the device. So once we have, now we have the whole geometric quantities of the isolator. So finally, we can compute the total number of isolators, which is through the computation of the single device, the single isolator stiffness by dividing the maximum force of the single isolator divided by the maximum displacement. And then we still have the number of devices, which is the ratio between the equivalent stiffness of the whole isolation system divided by the single device stiffness coefficient. Okay, and this is it for lead rubber bearings. You have seen that the procedure is quite similar to the one provided by the pure rubber bearings. We just need to consider also additional parameters because the overall behavior is a little bit more complicated. But okay, I try to provide guidelines based on realistic data for full-scale devices which have been experimentally tested. So there are actually distributions, probability distributions, and okay, in design we can directly consider the mode value as the most frequent, but then we can also try to perform some parametric study. Before the other two parameters which can be considered as random variables, I mentioned that the yielding shear strain, even though it is a random variable, this has a very little influence on the overall response of the base isolated building. Obviously, you can imagine that it is on the other hand, we have a high influence of this parameter on the overall response of the isolated building. This is the most influencing parameter on the overall response. So this is worthy to be considered as a random variable for parametric study. This could be also a very important parameter because generally there are some producers which obviously are focused on different materials and maybe can consider lower values of these ratios. So we can this is actually the mode. So maybe there are some of them which are in these regions, and some of them which are actually here. I think that as I mentioned before, we can consider values bounded between 0.5 and 1.5. But you will see by using this procedure through the Excel file. Actually, if you consider a smaller ratio, you will get a higher number of devices at the end. So this means that a lower value of this ratio will lead to a higher coverage, a better coverage of all the supporting points of the structure with directly isolators. Whereas if you choose a higher value of this ratio, maybe you will obtain less isolators and more flat sliders. Okay, so that would be an important information for your design, because maybe with some producer, they can say that you can analyze the catalog for their devices, lead rubber bearings, and you see that maybe the diameter of the lead core with respect to the height is 1.2, maybe. Okay, And you try to perform some design computations, and you get very few devices, which does not make a lot of sense, because okay, we can actually provide the definition of hybrid solutions, so the combination of flat sliders and lead rubber bearings, but at least there is a minimum amount of devices that you have to place, and in order not to obtain actually mismatch the results with respect to the initial design performance point. And so maybe you have to go to another producer with which actually leads to this ratio, which is a little bit lower value, so that you can actually provide much more devices with respect to the total number of structural supports. And I think that's it for lead rubber bearings. Are there any questions of the overall procedure? Okay.
It's okay, Doctor.
Okay. So let's finish this lecture about the procedures on the curved surface sliders. So you will see that maybe this is the most complicated from the mechanical point of view. I mean, solution for isolation devices, because the force response is a direct function of the vertical force which is applied to the device. We have the friction coefficient, which is actually a parameter, a mechanical property, which varies from the experimental point of view, so the realistic point of view, with respect to a number of response parameters. For instance, we have seen together in the experimental data processing that the friction coefficient varies with respect to velocity. We have already discussed yesterday that the velocity dependency is not so much influencing the overall response, but there is another dependency, which is actually the dependence of the friction coefficient with respect to the applied vertical load. That is much more important. And then we know also that there is the degradation of mechanical properties with multi-cyclic excitations. So the friction coefficient is a quite complicated parameter to deal with. And okay, these are the main characteristics for lubricated material and dry materials. So we have a very low friction coefficient values from 0.5% from up to 4% for lubricated materials. And for dry materials, we go from, we are bounded between the 4% and 15%. And then equivalent equivalent radius of curvature, they are bounded between 1.5, it is a very small value, 1.5 up to 6, they are extreme values. General values are 3, 4, 2.5, the minimum one, up to 4.5 and 5. 1.5 and 6, they can be used for very particular applications. With the lower they are equivalent, the higher will be the restoring stiffness. So the 1.5, you can imagine that the overall behavior of the device will be very comparable to a linear device, because the stiffness, the restoring stiffness is very high. Whereas as you keep increasing the equivalent radius of curvature, the overall device will be much more and more similar to a flat slider, because if you increase the equivalent radius of curvature, let's say if R equivalent tends to infinite, we get exactly a flat slider. So I think that for higher values, higher than 6 meters, the overall response can be directly associated to a flat slider, because there is no particular vertical motion, no pendular motion, and so the component, the horizontal component of the applied vertical force projected along the spherical shape of the sliding surface can be actually neglected. So again, we have the three steps, initial steps, minimum isolation period, assumption of the performance point, and the computation of the, okay, here there is written again, displacement and normalized force demands, but generally we know the third step is computation of global characteristics of the isolation system. So this means that we need here also the K equivalent isolation, okay? Always according to the expression of the period of the self period of a single degree of freedom oscillator. Okay, and then we have okay, we have seen we have 7 steps for the rubber bearings. Then we have 9 steps for lead rubber bearings. We have 4 steps for curved surface sliders. So in the first step, we have just 2 equations. The first one for the equivalent radius of curvature, and the second one for the friction coefficient. That's it. Okay, with just 4 steps, we have designed the mechanical properties of the overall device in terms of actually equivalent radius of curvature and of design value of friction coefficient. I just highlight that both the expressions, which are actually derived with respect to the maximum force definition and with respect to the definition of equivalent viscous damping. And both of them are functions. Okay, here there is G, which is the gravity acceleration, omega squared isolation, which is a direct function of the period, the design period that we assume in design for the performance point. Then there is Xi AC, which is Xi D. So I mean the equivalent viscous damping ratio. But then there is also Xi limit. Okay, and you see Xi limit is equal to 2 over pi, which is approximately 64% of equivalent viscous damping ratio. Okay, so what is this number actually? So this number is a very important number because actually this is the maximum damping ratio that you can achieve with an hysteretic loop. Okay. So whatever is the shape of your hysteresis, this is the maximum hysteresis equivalent viscous damping ratio that you can achieve. And it is actually related to specific behavior, which is actually the purely frictional behavior. Okay, and I just want you to see why it is computed as 2 over pi. Well, just because if we consider the purely frictional behavior in terms of force displacement loop, we know we have the hysteresis, which is just a rectangular shape. Okay, so let's consider again with respect to the Jacobsen formulation of equivalent viscous damping, a fully reversed cycle. Okay, and we know that this is actually the hysteresis for a purely frictional response. Okay, so let's try to consider the expression for the equivalent viscous damping ratio, which is EDC equivalent energy dissipated per cycle divided by 2 pi d max f max. Okay, we have actually derived this formulation also by considering some end computations, but this is actually what is known as the Jacobsen formulation for the equivalent viscous damping for a given hysteretic loop. And actually, if we have to try to provide an expression for the energy dissipated per cycle for this behavior, we should find actually the entire area of this rectangle, and this rectangle is exactly equal to 4 times the multiplication of d max and f max, which is actually this rectangle. Okay, so the EDC can be computed as 4 times the max and F max, and then we have divided by 2 pi the max F max. So we have 2 over pi. Okay, and this is called Xi limit, and it is called limit because this is actually the highest value of equivalent viscous damping ratio. With any kind of other shapes of hysteresis loops, you cannot achieve a higher value of the damping ratio. Okay, this is actually the maximum one. So 64%, 2 over pi. So instead of having 2 over pi's along the expressions, it is better just to see Xi limit. And this is just the ratio, a ratio among the different values of damping ratios, and the same here. And concerning the friction coefficient, you have to compute the displacement demand, and then the R equivalent, which is computed with the previous one, and then this the multiplication to this ratio of damping ratios. And obviously this, there is a question.
Yes, Doctor, this limit is regardless of the type, whether it is a triple, because they will have hardening. So this is applies everywhere, right?
Yes, actually, if you think about hardening, whatever typology of hysteresis with the hardening has a lower value of damping ratio, because actually by keeping approximately constant the energy dissipated per cycle, you are actually increasing the maximum force, which is at the denominator of the expression of the damping ratio. So you get a higher value of damping ratio, of equivalent damping ratio, as soon as you have something similar to a perfectly plastic behavior. So as you are reducing hardening, but there is even if you consider softening, that would imply a lower value of damping with respect to a perfectly horizontal hysteresis loop. Okay, so that is actually the maximum one that you can achieve. If you get if you consider hardening, you are decreasing the damping ratio, because you are increasing actually the maximum force by without changing actually the energy dissipated per cycle. If you consider softening, you are actually considering the same EDC, but I mean, you are considering a lower force, but you are also considering an increasing value of EDC. So it is a some way balanced, and this is actually the maximum value of damping ratio.
Thank you, Doctor.
You're welcome. And generally, okay, you see, this looks like the easiest fast design procedure for isolation devices, because we have just 4 steps. Okay, but we have to keep in mind that one device has been completely designed only if we have designed not only mechanical properties but also geometry. Okay, if we consider these 4 steps, the final result is that we come up with the device, generally the characteristics of the device in terms of mechanical properties. So we have the equivalent viscous, the equivalent radius of curvature, and then the friction coefficient, which are just mechanical properties. The equivalent radius of curvature can be directly associated to geometric characteristics of the device. But actually, we need more information about that. Okay, now the overall presentation is finished, but I have prepared some blank slides just in the case we need some additional explanation, and I think this is the case. for just curved surface sliders. I would just want you to see how to completely design the device, because with the design of CSS, so curved surface sliders, the design procedure allows you to compute the R equivalent, so the equivalent radius of curvature and the design value of friction coefficient. Okay, but together with these values, we know also the max, which is the spectral coordinate with respect to the displacement spectrum as a function of the assumed performance point, which is the isolation and the equivalent viscous damping of design. Okay. Okay, we have also the normalized force response, but actually this could not be this parameter could not be addressed to some geometrical characteristic. Yeah, the maximum displacement can be addressed actually to the geometry of the sliding device, because actually we have to design the lateral geometry, so the horizontal geometry of the sliding surfaces. So we have to allow that displacement, and so this is actually an useful information for the overall geometry of the isolator. So this, let's consider one by one these parameters. Okay, the friction coefficient does not lead to any kind of geometrical information. So this we will not use the friction coefficient. We will surely use the equivalent radius of curvature and the displacement demand. So concerning the equivalent radius of curvature, these can be associated directly to the radius of curvature for the main sliding surface, but only in the case we are adopting a single curved surface slider. So with just a main sliding surface, and then if there is another sliding surface that is a secondary surface, so which is directly which can be associated to a hinge behavior, which just allows horizontal deformation to the main surface. Okay, but then the R equivalent is becomes actually a very important information when we have double curved surface sliders. So if we have two surfaces, maybe with non-articulated sliders, so the internal slider is just a unique steel block. So this information to become a real geometrical property, this should be should need actually additional details, which means do we have to consider single curved surface slider or double curved surface slider? Okay, because if we have this particular typology of device, maybe we have something like this, as we have seen in the previous lectures. We have just a hinge, and then we have the main sliding surface. So the equivalent radius of curvature is directly the radius of curvature of the main surface slider. So this is equivalent radius of curvature. So the radius of curvature of the main sliding surface. So if we have a double curved surface slider or double concave, there are other names for such a typology. Maybe let's consider the prototype that we have seen in the previous slides. So I mean this one. This is a double curved surface slider with a non-articulated slider. You see that this is a unit steel block, and both the surfaces have exactly the same radius of curvature. Let's consider this typology, and we have so something like this. Okay. Okay, with R, and this is also R. And the height of the internal slider is small h. For this case, you will find in the literature a lot of initial research articles by Professor Michael Constantino of at the University at Buffalo, who is actually provided the patent of this technology. The equivalent radius of curvature, which is actually the mechanical parameter to consider for the hysteresis loop, this is equal to, for this device, 2 times R minus H. Okay. So depending on the this assumption, so depending on the typology of isolator that we want to consider, curved surface slider, I mean single or double, we have this information of the equivalent radius of curvature can become just directly the radius of curvature of the main surface, because the other surface is just a hinge for the single curved. For the double curved, if we assume the same radius of curvature for both the surfaces and a unique steel block as an internal slider, we have exactly this expression. So by assuming the height of the internal slider, we can compute the radius of curvature of the surfaces, or vice versa. We can guess an initial value of the radius of curvature for the sliding surfaces, and then we can compute the height of the internal slider. So there are two different ways to translate actually this information, which is actually a mechanical property, because the R equivalent provides the restoring contribution in the force response, and but we know that this automatically implies a certain typology of geometrical configuration, and this is strictly function of what we assume as main typology of device. Okay, and finally there is also another the very last I mean two last informations for this typology of isolator, which is again the curved surface slider. So you see that we have 4 steps for the definition of mechanical properties, but actually we have a lot of issues to consider to come up with the final geometrical configuration. So it is quite straightforward. We can stop at the 4th step whenever we have just to define the environment for nonlinear time history analysis, because we don't have to care about the geometry of the device when we have to carry out nonlinear geometric analysis. Nonlinear time history analysis, because we just need the hysteresis loop. But if we want to consider the final result of the device, we have also to define the plane sizes of the isolator. This is one issue, and the second issue is the diameter of the sliding pad. Let's say pads, because we may have more than one. So what about they are obtained from 2 different parameters. The first one, plane sizes of the whole isolator. This is strictly a function of the displacement demand. Okay, and simply because, again, it is also a function of the typology of device that we want to design. So if we have the single curved, single curved surface slider or double curved surface slider. So we need actually to provide the the main sliding surface to be large enough to accommodate the maximum displacement. Okay, so this is the displaced configuration, and it would be here. This should be the maximum. So this diameter should be large enough to accommodate this displacement. Okay, so by drawing the overall device, we can just design the overall geometrical quantities in order to accommodate this displacement demand. With these particular typology, if we consider the double curved, we have obviously a different behavior. The displacement is the same, but actually we can have a different geometrical configuration of the device. So we have this is the max. And generally what happens is that if we consider the same displacement demand, the geometrical configuration of the double curved surface slider is smaller than the geometrical configuration of the single curved surface slider. So if we want to save space, we would go through a double curved surface slider by considering the same displacement demand, because generally you have to achieve larger, I mean smaller devices. Then you achieve the same value of peak displacements, but the device itself is smaller if you consider two sliding surfaces with respect to one. Okay. And actually, it is like this because you gain the maximum displacement in two individual surfaces rather than this first device where you have actually the total amount of displacement basically on the main sliding surface. And finally, the very last geometrical quantity is the diameter of the internal slider. And let's consider this is actually an information that can be is applied to both these typologies of devices, and this is directly related to the response to the real response of the sliding material which is adopted, because generally we know that the isolator is subjected to a vertical load, and then together with the vertical load, I mean, this is the diameter, the internal, diameter internal, and we have W, which is the applied vertical load. We can compute a pressure, which is the internal contact pressure, the average one, because then there would be some variation in the distribution of the contact pressure. We had the occasion to provide some evidence, some experimental evidence of such distribution as zero displacement configuration of the prototype of device that I've shown. There are some details in some of my papers, especially one of 2019 of in the journal Soil Dynamics and Earthquake Engineering. But generally, for design, you can also consider directly an average contact pressure, which is constantly smeared on the area of the sliding pad. So it is computed through the ratio between the applied vertical load and the area in, I mean, in the internal area, and the internal area is just the area of the circle related to the sliding pad. Okay, and then we know maybe every material has a proper definition of friction coefficient decay with respect to the contact pressure. This is in megapascals, and this is given by producer. And actually, this is something like exponentially decay. And maybe we get some sort of asymptotic value after a given value of pressure for PTFE based materials. We have that we can consider a constant value of friction coefficient, approximately constant, if we consider pressures higher than 30 megapascals and the maximum pressure is 60. Okay, so the applied vertical force is actually a function of gravity loads which are applied to the structure. That could be also that parameter could be also a function of the overturning effect during the seismic event rather than actually the vertical component itself of the seismic event. But once we have an estimation of the vertical component, I mean of the vertical force, we can come up with the area of the sliding pad and then consequently to the diameter. If we assume a contact pressure value, a design value for the contact pressure, because maybe we want to consider a value which provides a fairly constant value of friction coefficient afterwards. Or maybe we can also choose an intermediate value. Maybe we can choose 45 megapascals, which is actually because maybe we want to consider also that we have fluctuations of the vertical load due to I mean overturning effects rather than vertical component. So we want to be here in an intermediate point, so that if we move back and forth due to the effects that I've mentioned, we keep the friction coefficient approximately constant, so that we are in a certain way ensuring that the overall behavior will be constant associated to the frictional properties. So this is another parameter that has to be ensured by asking to the producer of the sliding materials, which has actually, we should have actually a full characterization of the vertical load effect, so the dependency of the friction coefficient on the contact pressure. What I meant in the previous lectures with the vertical load effect was actually this issue. So the friction coefficient is not directly dependent on the vertical load in terms of value in kilonewtons, but it is directly a function on a function of the contact pressure that we have on the material, and then if we multiply the pressure times the area of the material, we get the vertical load in kilonewton. So the dependency, the real dependency of the friction coefficient is with respect to the contact pressure applied to the material. And then once we have defined this, okay, now we have also all the informations of the also from the geometrical point of view. For the curved surface sliders, and that's it for the overall fast design procedures. I think we are at the end. We will use these procedures for the case study structure that we are going to, I mean, to define on Monday. On Monday, I think that we will be able to use the sub 2000. We will do some end computation at the beginning, but then we will immediately model through the software the building, and we will do also the modeling of isolators and so on. So again, I just want you to send me an email in the case that you need the access to the software. You don't have your software, so I can provide the access to the computers that I have in my faculty, which have actually already installed the software SAP 2000. just email me and I will give you instructions within Monday morning. Related to this lecture, is there any question? Something not clear?
Yes, Doctor. I just want to ask about the maximum displacement. This is for double concave and single concave, but sometimes in the case of hardening, this value should be before hardening, isn't it? Like the maximum design should be before hardening of the.
Well, actually, you start with this typology of device. You start having hardening as it starts moving, because the hardening is provided by the projection of the vertical load along the tangent plane to the spherical surface. So this means that once it starts moving, the vertical load is projected along the curved shape of the spherical surface, and then this is the reason why you have the restoring stiffness for the hysteresis loop. So once you get the maximum displacement of the device, you already have the hardening from the beginning, because from actually after having overcome the frictional force, you start moving, you start the sliding motion, and as you start the sliding motion, there is already the recentering contribution, because the spherical shape provides the stepwise projection of the vertical force.
Okay, Doctor. Thank you.
You're welcome. Other questions? Okay, so we are at halfway of this short course. I hope that you are enjoying the information of the course. Okay, exception made for last Wednesday. This was the first week among the two of duration related to the most part of the theory. Okay, we did a lot of practice also on Wednesday. But generally, yeah, there will be also some information, theoretical information also next week especially for the selection of input signals for nonlinear time history analysis on Tuesday. But then it will be actually much more practical. Again, if you think that since we are at halfway for the short course, if you think that I'm going too slow or too fast, just ask me, and then I will try to adjust the lectures of the remaining days. So I think that's it. If there is no other question, please email me if you need the access to the software for Monday, and see you on next Monday for the implementation and the modeling of the case study structure. Have a nice weekend and have a nice day.
Thank you, Doctor.
Goodbye.
Bye-bye.